This is the really great Carbon 5 programming languages get together. My name's Quinton Harris. It is a moment in time. And actually, as of right now, we are frozen in time. And we're going to talk about that a little later. So the language in question is called ChucK. And it's a language that's intended to serve as a basic, as very low level building blocks for generation of audio, but with a lot of room to scale up into some high level logical structure. Cool. Let's get into it. First, a bit of computer noise over time. Got to have the historical context here. Humans have been trying to make music on these contraptions for many decades now. The first generated music was on an Australian supercomputer, or what qualified as, I guess, a supercomputer in 1950. This cat, Trevor Percy, just spat out like raw signal pulses, just like raw voltage to a to a speaker, and ended up making noise that I'm sure would be considered pretty contemporary and avant-garde by the noise court community. Next iteration of note is Max Mathews working at Bell Labs. So in '57, he released what he called music at the time. This is later annotated as Music 1. And over the next 10 years, he would release different versions of music up until Music 5. This is pretty important work and is the foundation of a lot of strategies that were picked up by Max MSP, ChucK, et cetera, and these strategies are continuing to be used today. Next event of note is Miller Puckett working over at URCAM. URCAM is a French institute dedicated to the research of sound and music, especially focusing on the avant-garde. So computer music is, of course, a likely topic for them. So he put together the Patcher, which is a prototype for Max. And we'll get into that a little later. In 1991, he releases Max and MSP. And MSP is the Max Signal Processing suite, which is a corollary to Max, whereas Max deals with controlling control messages over time, like MIDI. MSP is dedicated to signal processing in the same way that Max does. We'll get into this a little later. 1996, between 91 and 96, some licensing stuff happened. URCAM licensed the Max code to a company called Opcode over in the Bay. Miller Puckett left and rewrote Max MSP as PureData. So PureData is the open source port of Max MSP. Also in 96, Supercollider was released, completely separate language from anything else, and is pretty nifty. We'll touch on that shortly too. And finally, in 2003, we have ChucK released. Cool. All right. Oh my God, I'm sorry. I'm like clicking on the thing. Let's get into the next. Right. So Max Mathews, music. He's over there in Bell Labs. First releases music in '57. 10 years later, Music 5. This is really the first language to generate PCM samples. PCM is pulse code modulation. This is how audio data is encoded onto pretty much anything, like CD players speak PCM. WAV files are the de facto portability format for PCM data. And it kind of pioneers this two-file paradigm, right? So there is a suite of the language that is dedicated to the sample rate, and there's a suite of the language that's dedicated to the control rate. So what do these things mean? Sample rate is, okay, so right, due to the Nyquist frequency and whatnot, we need to generate some 44,000 samples per second in order to make a signal that sounds normal to a human. Their ears max out at 22,000 kilohertz. So crank that up to 44,000, and then you can make music that sounds normal to humans. So that's the sample rate. So that's how these operations are happening 44.
This is like the frequency of the sounds being generated, essentially.
That's correct. Yeah, yeah. So literally, what you're doing is, if you can do some crazy analysis on a sound wave, you're going to see it, oscillations over the course of whatever frequencies, right? But you can translate those into like amplitude over time, and so that's music, and that's the sample rate. So then on another track, there's the control rate. So the control rate instructions operate on whatever is generating the samples. So typically, the most basic example might be like, okay, in the sample rate land, I want to declare that I have an oscillator that is connected to the digital out. So maybe like a square wave or something. And then the control rate's going to say like, okay, Mr. Square Wave, I want you to play at 440 Hertz for 3 seconds. So somehow that passage of time happens in this programming language, and music is generated. Right, okay, yes. And right, opcodes are the unit generators. They might have no inputs. They might have a sample rate input. So you could, something like a filter could be considered an opcode. These can be composed into pretty complex virtual instruments. Yeah, and control rate is there. Right, so music, the music suite pioneered a bunch of strategies. Lookup tables for waveforms and envelopes. So something that might be expensive, some sort of like Bezier calculation is just, frozen into a lookup table and improves processing time significantly. He's a pretty cool dude, this Max Mathews, and he's responsible for a lot of the tools that we use today. So props to this fella. Okay, a couple quick notes about Supercollider. This was released just on his own by James McCartney after, I guess, working in Las Vegas doing a bunch of performance-related programming for many years. So he just fired this up just as for fun before joining the Core Audio team in 2002. He spent about 15 years there making OS X awesome. The client-side code is pretty similar to Ruby and Smalltalk with a lot of syntactic goodies. It's pretty rad. It's dynamically typed, first-class functions, list comprehensions. It's a blast. Since version 3, Supercollider's architecture has split into like a client-server paradigm. So you can have this virtual machine just running, and then whatever number of clients like connecting to it and saying like, hey, set up an opcode. Hey, with these virtual instruments that I've defined, go ahead and play those. This OSC layer enables things like live coding, advanced GUIs. So I could create a GUI in TK or whatever you want. OSC notably is the open sound control. It was intended as like a networkable and an extensible structure for MIDI-like messages. So I want you to, hey, for synth number 1, 2, 3, play this pitch for this time. That can all be compressed into one word. Whereas to achieve the same effect in MIDI, you're going to have to do a lot of things, at least 2 messages, right? Note on and note off. And somehow you're going to have to keep track of time in the meantime. Let's take a look at some code here. So this is a complete Supercollider program. You can see I split it up with line numbers accordingly. Over here, we have like the sample rate declarations. So we're going to say, hey, I want to set up this synth named Gabber Kick. We're going to assign it a frequency. We're going to do a bunch of other stuff. And yeah, we're going to tack this into whatever the unit generator graph. So we set up our samples over on this side. And then over on the right side, we have a bunch of control rate data where we say, okay, we want you to play this instrument at this amplitude. for this duration, and play it on a clock. And this is a pretty high level screenshot I grabbed, but I think it illustrates Supercollider pretty well.
Definitely looks like Ruby or Smalltalk.
Yeah. You got to see the other stuff. It's rad. Okay, moving on. Brief overview of Max MSP and PureData. Max MSP is a visual programming language. It's a GUI layer over this data flow paradigm where messages are just, you compose a big signal chain of like logic gates and all these modules that take some input and spit out some output. So all of your RX programming skills are going to come in super handy with Max MSP. Max, when it was originally released, maybe as the patcher, this was control rate level programming only. So it was implemented typically as kind of a MIDI Swiss Army knife. So say you had a synthesizer that had a lot of like system exclusive functionality that you don't have a control surface for. If you wanted to, you could pore over the documentation, read all the sysx, messages, set up Max to compose these and translate whatever fader values from your normal control surface into these sysx messages. This is all possible. It's sibling MSP, our signal rate. And so you have signal rate opcodes, same as in Supercollider. You have unit generators, you have filters, et cetera. One cool thing about Max MSP is that there's a kind of seamless delineation inside a Max file between control rate and sample rate. You can see like the lines of each signal are kind of describe what signal it is, whether control or sample. We'll get into that in a second. But notably, Max MSP was used to prototype Ableton Live, which ended up buying out Max MSP, I think in 2017 or so. If you're interested, Sam Nazarin also gave a presentation on PureData specifically. So read his, view his slides for a better demo. So let's just take a look at some code real quick. Yes, this is Max MSP. So we can see here, yeah, actually, this is a great example. These black lines are all control level signals, whereas these dotted lines are sample rate level signals. Yeah, it's difficult to read, difficult to refactor. This is the actual, this is like a serialized Max file. This is just a plain text, file describing your Max patch. So if you are, for some reason, on version control and your buddy decides to drag this box to the left of one of your boxes, be prepared for a very, very fun merge conflict.
Does
cool.
the file records the position or just the connectedness?
Both.
Okay. So it says this box is here and connects to these things?
Yes. Yep. Yeah, it ends up feeling pretty unmanageable very quickly. Okay, let's get into ChucK. So ChucK was first released in 2003. G. Wang was getting his degree at Princeton and worked closely with Perry Cook to develop this language. It was inspired heavily by Max Mathews and Music 5 in particular. It's typed and it's strongly timed. We'll get into what strongly timed means a little later. So it's an audio generation DSL that intends to expose, it's a funny mix of like low level and high level paradigms. It executes on a virtual machine. The ChucK code compiles down to bytecode, which is then interpreted by the VM. The VM, during that interpretation step, has a whole like signal level cloud of unit generators that we'll get into in a little bit. Yeah, that's kind of the broad strokes of ChucK's execution. We have native time and duration types for interacting strongly with time. And they put a lot of work into concurrency. So we have this notion of deterministic concurrency, which is pretty fun. I think typically with normal thread-based concurrency, you kind of don't know what's going to happen when. Yeah, race conditions are common. This is not the case with ChucK. ChucK's Shredcellent keeps the ChucK shreds in a row and make sure that they execute the right instruction at the right time. And we'll get into all that further on. The primitives of ChucK actually are pretty simple. So here we go. We have a couple types for interacting with numbers, a couple types for interacting with time, void for your functions, a couple convenience types, notably a vector of floats, in case you're doing something in 3D, I guess, or 4D space. And complex and polar, I have never used these. I know they exist. I'm sure they're implemented for a reason. I also don't have a career in working with ChucK, so I can only assume that these are very useful. But I do appreciate these little template literals here. Pretty fun. Okay, so does void mean?
Void means void, right?
Void means void, yes. Yeah, you can't do crazy, void star stuff. And you wouldn't want to in this world. Hi, Konyo, sorry. Okay, getting into operators. I think the king of ChucK is this beautiful directed arrow, AKA the ChucK operator. They've overloaded this in clever ways to really make the DSL expressive and pretty easy-ish to work with. So you can see here, they've done a number of sugar assignments here. Notably, we do have this at ChucK, which is explicit assignment for reference types. So you can do pointer arithmetic. You can shoot yourself in the foot if you want. It's pretty fun, but typically you don't need to. This is brought in when you instantiate a class or a UGen or something else. Standard arithmetic, we have a modulo, bitwise assignment. These are all backed by standard C or arithmetic, bitwise, and logical operators. So you can expect to see multiplication, division, logical and, bitwise and, et cetera, and a couple fun features like destructuring. Say foo is some vec, and you want to destructure that into floats 1, 2, or ABC. You can do that here. Okay, right, strongly timed. What does that mean? So yes, it's a very cute wink and a nod to strongly typed languages. But in ChucK, what this means is that you are going to explicitly indicate the progression of time. So with most programming languages, say like C, you're like, well, I know this is going to run fast. With maybe something interpreted and super heavy weight, you're going to say this is going to run slow, but it's fast enough for my needs. Not so with ChucK, because we're dealing with the composition of music. If your synthesizer was going to hang in the middle of an operation, that would be very bad for your performance. So what we say is we're going to iterate time explicitly. So, and this is achieved by throwing a duration to chucking a duration over to now. So this is a valid ChucK expression where I'm saying, hey, iterate 3 seconds to now. We'll see how this interacts with the signal graph a little later. This has the fun side effect of like making event handling like super expressive. So say I have my event and I say like, okay, this event is going to wait on a keyboard press of whatever, the plus sign or something. Well, when I want maybe I say like, okay, I'm going to sleep until this keyboard event. You just say E to now. So this is not going to fire until you like touch your button. and then suddenly it's now everything after this line is going to occur directly after that keyboard event. So the dev cycle typically ends up being like you start up your ChucK instance. You set up your signal chain. Say like, okay, I want to create a flute patch that has a desired pitch. It's going to play at A440. And then finally you say like, all right, go ahead and play for 3 seconds. A flute sound at A440 will occur for 3 seconds. After that, depending on how your file is structured, maybe the program ends there, and so the sound ends there, or you're on some like, you know, while true situation. It could be actually that you don't even. No, I don't want to say that. Yeah, you could be inside a while true where you're iterating like 1 second forever, and that would have the flute sound play forever. Multiple ChucK files can occur at the same time, and they can all change and iterate on time in different ways. And this is all magically scheduled via the scheduler. And through this deterministic concurrency, you're going to get guaranteed correct audio, even if it can't be performed in real time. So if you're crunching a bunch of Dogecoin or something and your, you know, nice mode is off, ChucK is like, no problem. Like, it will serialize your audio data into a WAV file that you can play back later. So it's pretty versatile. Okay, I think we know enough to get into the examples here. So this is like a very basic example. We have a sine wave oscillator that is ChucK assigned to DAC. This is digital audio out. We crank down the gain on this significantly because they can be quite loud. And then we get into our while true. This T is kind of a convenience tracker of time. We'll see that in a second. But we have a sine wave going. Then what we're going to do is assign to the frequency of this sine wave some fun math, some oscillating math. Okay, so we take a base frequency of 100 hertz. We take the sine of T, multiply it by 1000 to get something interesting sounding. We'll iterate on T just a little bit so that this sine calculation will be different next time. And then we kick off 1 millisecond. And then we go through this again. So you can kind of see, I'm not good at my eyeballed periodic functions, but this is going to sway somewhere between the order of what, 1 to 1100 hertz.
So well, yeah. So the sine's going to go from -1 to 1. So +1 means 0 to 2. And so 0 to 2 times 2000 is 0 to 2000. So 100 to 2100.
Yeah, there we go. Thank you for that. Cool. So this would make a sound that we might hear a little later.
Can we go back?
Yes.
That was okay. So this is saying we're going to define the frequency of this oscillator by this function of T. And then each loop, we're going to add 50 or 5/100ths to T and then play that thing for 1 millisecond and then switch it and keep doing it. Okay.
That's correct. Yeah. Moving on into something a little more crazy. I can't really explain this 100%, but the ChucK guys are very excited about this. This, I think, is a simulation of like a sitar or a guitar string that is resonating like according to itself. It's a feedback function. I don't want to burn the time trying to give you a poor example of how this works, but but it's pretty wild. So take this as homework. It's available in the ChucK examples under the deeper stuff example section. And we'll listen to this a little later too.
Ari said something in the chat.
Oh, what did Ari say? Car plus strong. I believe that's right.
Oh yeah, that's a good easy string, like, you know, simulation algorithm. It's cool. Should try it.
I played the file. Can't say I understand all of what's going on, but car plus strong. Cool. Okay, moving on. Okay, so those are two examples. Classes are available in ChucK, and they're kind of a big deal. It's single inheritance. We have static data and functions available. Some notable examples are the object class, the event class, and Shred class. They're all built in. There are some built-in unit generator classes. So these might be your SYN oscillators. I think we'll get into that in the next slide. No, we're going to get into concurrency. We'll come back around to unit generators. Concurrency via shreds is expressed via this fork tilde whatever function I want to be created as a shred. The shreds can share data via global variables. And how do shreds work in concurrency? So right, at some point a thread needs to say, hey, I'm like done, you know, doing my little bit of work. Well, I'll let my neighbors have a chance. And this is achieved pretty like under the hood via whatever the iterations onto now are. So if you had a shred that like never interacted with now, it is very well potential that you'll get like a hang, and nothing will, basically no audio will happen, will occur. If you have a VM running in some friendly environment, they'll let you know. The VM will say like, hey, I think we're hanging, like nothing's happening here because I'm not getting that yield from the shreds. And then you can say, oh, okay, I forgot to iterate onto now. A different way to yield is this magic me.yield function. Me is a special, it's kind of like this for JavaScript. But you can say, hey, I know that I am a shred and I would like to let my other shred neighbors have a chance to perform any operations they need to do. Yes, no time will have passed. So you could do 3 seconds until now, me.yield, and then iterate another 3 seconds. The scheduler will take care of all of that. Everything happens at the right time. The right piece of code is executed at the right time via the scheduler. In the case that you have some crazy computation that's going to set up like that might like otherwise like say you had to calculate pi out to the millionth digit or whatever, the like scheduler takes care of that like ahead of time, so that like you're not like, oh my god, I'm going to do some really heavy computation like right now. The audio is still guaranteed to be correct. Right, Synth Guts. Okay, yes, so we talked a bit about UGens earlier. UGens are pretty important because that's how the sausage is made. So we have this UGen graph of, it's just a bunch of unit generators all either composed or mixed at the end of a signal path and spat out to typically audio out. So it's a per sample audio signal. And some, let's see, notable unit generators are ADC for input. So we could take a microphone input and do interesting things with that. We have basic oscillators. These will be familiar to you synth nerds. We have a sound buff for reading samples off your file system. Filters, there's normalize operations. They're pretty like standard toolkitty, whatever, signal processing. And then kind of a standard library, the SDK. We have some like a Whirly, we have a Moog patch, sitar, and et cetera, et cetera. I think Blowhole is like the sound of air over a beer bottle. And then finally, DAC for output. Cool. So what does that all look like? So this is pulled from the ChucK documentation. But you can kind of see, so right, at the heart of it all is the Shredcellent. And next to it, right, inside the audio engine is this UGen graph. And this is kind of probably the most important part. So what ends up happening is, the scheduler is going to pick some shred to execute for like this piece of time. The shred connects to the UGen graph, operates on whatever, UGens it's concerned with, right? Say maybe like this little box is my flute patch, and I want the flute to now play high C instead of middle C. So the shred is going to say, hey, you change your, intended pitch, and this box might be some vibrato oscillator saying like, well, actually, no, it's just going to be a gain box. So you say like, hey, Mr. Gain, you are simulating a vibrato effect. So take the result of this periodic function and modulate the gain on this flute accordingly, et cetera, et cetera. So the shred issues some number of instructions to the UGen graph. This UGen graph then processes the next sample and spits that out. And then 1 millisecond or 1 second or whatever has passed. The scheduler then says, okay, who's up next, right? Who is concerned with this like moment in time? And picks the next shred and rinse, repeat. Right. There's also a compiler that is like shooting new shreds into here. This will like complain to you if your thing isn't right and can't compile. That is the super loose example demonstration of what's going on. Let's see. Up next is MiniAudicle. So it's possible for you to interact with ChucK like on the command line. You can just say, hey, ChucK, run this file, and it will dutifully either fall into your while loop, or it will set up your flute patch, run for 3 seconds, and quit. But ChucK was designed for more than just running sounds off your file system. ChucK was designed to assist with live coding, which is it's jamming in code. So say you want to make a funny sound, but you don't know how to get started. Well, you just start with whatever, a noise signal generator and a filter and go from there, and iterate upon that while making sound. So this ChucK IDE MiniAudicle was set up for that. So here's a screenshot. It's consists of this virtual machine window, which is a quick little like eyes on the VM. Notably, you can see the number and name of shreds that are being executed. These correspond to these documents back here. The documents have some pretty nice like UX features. So like this big plus is like, hey, I've written all this code. I want to see how it sounds. All you do is just click the plus. If this is a shred with like with no chance to escape, so a while true, you have the handy replace shred button, which can just take whatever is running previous, the previous implementation in your file, replace it with this current, like compile and replace it with this, and you can remove this shred. It's pretty intuitive and fun, I gotta say. It is subject to hanging, and the IDE will tell you when the shreds hang. But all in all, it's a pretty fun little workflow. A brief note about the project history. It was super active in 2003 to 2008 because G. Wang was getting like his degree based on this work. And then after a decade, received a pretty big refactor in 2008 to improve embeddability into different systems. After working on ChucK in 2008, Ji Wang went on and was one of the members of Smule, who notably released IMT Pain, if you remember that iPhone app back in the day. That was pretty cutting edge, like signal processing for the iPhone at that time. So Ji Wang had to he had to chase that down. But then recently in 2021, in April, a repairathon and a new dev roadmap was organized by both G and Perry Cook. So there's a bit of interest from the creators, which is a great sign. We're now at 1.4.1 and more to come. Cool. So last thoughts. This CMJ article is linked from the ChucK website. It's a fantastic read. They go into much more detail, much more detail there. So please read it. It's great. Okay, discussion.
Ask questions, people.
Yeah, Ari.
Why did you choose to do ChucK over, let's say, Supercollider?
ChucK is easy. It was new, and it had a bit of buzz back in the day. I was mostly at like playing with it around like 2004 to 2006. Supercollider is pretty hard. Supercollider is not easy to make sound good immediately. Whereas ChucK, I think, first off, I think, yeah, ChucK is just more facile, and the dev cycle is a little nicer. Supercollider similarly has kind of that like live code, like replace shred functionality. It's just not as expressive. It's just not as easy. So if you can master it, it sounds awesome. But I found ChucK easier. I think I saw Will had a hand.
Yeah, have you written any songs in ChucK?
A couple pretty rudimentary tunes. They writing out like extended like harmonic, whatever, structures is pretty laborious. I think if you wanted to make a composition, your best option is to combine ChucK with like some music. What do you call them? Not an ID, a DAW. So say like Logic. So if you could route, I think through like internal MIDI routing, you could set up your signal chain in ChucK, and then have that await MIDI instructions and translate those into audio out. That'd probably be the easiest way to compose with ChucK. You can certainly, whatever, MIDI certainly is math and then can be captured inside numbers, but it's just not fun to read. Like this is not easy to read. So the music that comes easily is kind of like noise or random based music. I know there's a big trend of like generative music where like a composer would be like, oh, I have some thermometer on the network that is like transmitting how cold it is in Antarctica right now. Let's like assign that to the pitch of whatever, some synthesizer. That's pretty common, and ChucK plays nicely for that kind of work. Yeah, Miguel.
Yeah, you mentioned Max earlier,
Mm-hmm.
and I have some experience with Max from a computing music class that I took, and in that class it was like a lot of CS students and a lot of music students, and I found that the music students really liked the visual aspect of Max, and that worked well for them. So I'm wondering, who is this catered towards?
I think similarly, yeah, like Max, is intended to be approachable like to anyone. I think probably the basic assumption is that you're vaguely familiar with MIDI. And I think if you can handle MIDI, if you can handle plugging, one port into the other, then you get the paradigm, right? Signals flowing from one box to the other, and then it's just a matter of composition on top of that. Yeah. Let's see, Ari.
I'm always curious with these languages and stuff, like how do you, and you may have answered this before when you were talking about like random types of sequences, but like how do you interface with like musical rhythm? I think that's always an interesting question with these. So if you want to, let's say like you have your kind of like play loop and you want to play something on every 8th note or every 16th note, if you're using like Western notation as a guide, how would you go about doing that? Or is it even, I assume, I used ChucK a long time ago, but I don't really remember like that anything really.
Yeah.
Yeah.
Well, I mean, yeah, rhythm is repeated events over time. So yeah, if you wanted to do like 16th notes, you would take your, I think, perform some arithmetic on your target tempo. And
Okay.
then, I think probably, maybe the most
Pretty
basic,
low
right,
level. Yeah.
would be something like, hey, assign a random pitch to my flute out, and then iterate time according to, 100 beats per minute divided by 4 divided by 16, or no, divided by 16. And then just keep, so like change the pitch, iterate time, loop begins again, change the pitch, iterate time. So if you wanted to do something like staccato, or if you wanted to get more freaky inside that, you could say, change the pitch, iterate time a little bit, stop the sound entirely, iterate time a little bit more, then go to the top of the loop, turn the synth back on, change the pitch, iterate time, et cetera, et cetera. So it gets complicated if you want to do those kinds of like complex rhythms, but
it's pretty low level. That's interesting. Yeah, it doesn't have like events or anything like, oh, like on this division do this or something.
Nothing built in. No,
Yeah.
I think internal metronome type. I think it's expected that that is an exercise left to the reader.
Yeah. Interesting.
Sam.
Are shreds totally independent, or can they kind of like talk to each other? Can you like kind of do your timing in one shred, or do some sort of like a pulse in one shred and then kind of like react to it, or are they sort of just things you kick off and then they do their thing?
Yeah. So shreds can communicate via global whatever memory space. Let's see. Do I have an example? I'm sorry. Let me see if I can find the slide here. I don't have it. Darn it. Actually, but I'm sharing my screen, so I'll just show you guys right here. Oh my goodness. Here we go. Where's the file? Oh my god. Am I crazy? Okay. All right. This IDE is, yes, not working with me. So let's just go back to the presentation. So shreds can communicate via the global memory space. They can, I think, talk with each other through events. So you could like set up maybe some global event, have one shred listen on it and have the other shred like fire it. I think that could be a way for like, whatever inter-shred message passing. Yeah. Does that answer your question?
Yeah, thanks.
Yeah.
Good. Does everybody have their questions answered? Well, thank you, Quinton. This is cool. I feel like there's this trend of music programming language presentations, which I think is fun. And I really don't have any experience with it all, but probably should. So if you want to like bother me and say, Lindsay, let's pair on ChucK, I will say yes.
Yes. Awesome. Well, thanks for the opportunity to present.
Yeah, and I think next year we're probably going to switch to like nth day of the month instead of this 3-week thing, because that's confusing. But thanks a lot for presenting. I didn't have anything else for today, so I'm glad that somebody was like, hey, I want to talk about this thing. So, but yes, cool. Thanks a lot, Quinton.
Yeah, thank you.
Yes. See you all. Enjoy your Tuesday.